In this video, I will spend a few minutes talking about an apparent paradox that our textbook is discussing. So what I have here is just wires. These straight lines that you see with the orange color, these are wires that I have connected. And here I have a switch. So what you see, this part over here, this is my switch, and this can be either at A or B. Now, if you want, I can also add a light bulb here, and that will allow me to detect whether there is current flowing in the wire or not. Now, instead of a bulb, you can think about using an ammeter to measure the current, whatever you want, so long as you can detect the presence of moving charges. Now, what you see here, though, that's somewhat transparent with purple, this is my magnetic field. I have a magnetic field in this area. Now, I want to examine this case theoretically, the case where I move the switch from A to B. So what I'm gonna do, I'm gonna take it and move it here. And I want to see what happens if theoretically there should be current flowing through the bulb, if I should see light in the coming from the bulb or not. Now, I have mentioned there are two different cases where we can have an induced current. Case 1 is due to the presence of magnetic forces. Case B, is when we have a non-Coulomb electric field. These are the only two ways with which we can end up having an induced EMF and induced current. So what I will see if one of these two cases, in which one actually may give me an induced current. I'm going to start with the first one. I know that magnetic forces, to have a magnetic force, I need to have charge, and I need to have a moving charge in particular, and these moving charges need to be inside the presence of an external magnetic field. Now, because these are wires, of course, I do have mobile electrons anywhere in the wire. Okay, these are conductors, which means there are mobile electrons everywhere. So I do have a charge. Now, the thing is, these wires are not going anywhere, they're not moving. I have them lying on my workstation, on my desk, and they are completely stationary. So these mobile charges are not really moving, which means the velocity is 0. If the velocity is 0, then this means that there is no magnetic force. And of course, that means that case A is not an option. Magnetic forces cannot result in a current flowing in the wire. In any case, whether you switch from A to B, or you leave it always at A or always at B, no matter what you do with the switch, the velocity of the mobile charges is 0, the magnetic force is 0. Now, the second case is if we have a non-Coulomb electric field that will result in the induced current. Now, we know that we will have a non-Coulomb electric field if and only if the external magnetic field changes with time. But what we know from the problem is that when whatever you do with the switch, whether you leave it at A or move it to B or back and forth, whatever you want, the magnetic field, this external magnetic field, is a constant. And when we have a constant magnetic field, one that is not changed with time, this means that there is no non-Coulomb electric field. Because to have this one, you need a B as a function of time. but the external magnetic field stays constant. And if it is constant, there is no non-Coulomb electric field, which means case B is also out. So since there are no magnetic forces and there is no non-Coulomb electric field, when you move the switch from A to B, there should not be an induced current. This is extremely important, and I want to point out the process, the thinking process I used here. I used the actual physical mechanisms, okay? Not any equation. I used the actual physical mechanism to decide, to find out when I move the switch from A to B, whether there should be a current, an induced current or not. And using the physical mechanism, of course, at this point, using this process, we use fundamental physics, fundamental concepts and ideas to find out what how nature works. This cannot lead you in the wrong direction. Now, what would be the wrong way to think about this? Okay. We have seen that we have this expression for Faraday's law. Or if you want, okay, whatever you want, whether the change or the infinitely small d phi over dt, sorry, this would be a d, whatever way you want to think about it. If the only thing you use is this expression that we have in Faraday's law without really thinking about the underlying mechanism, this will get you to the wrong conclusion. Because when you move the switch from A to B, one thing that you see, okay, well, this is the flux. Let me show you. This will be the flux. This is the area that includes a magnetic field when the switch is at A, and when the switch is at B, you actually include the whole thing. And then this may make you believe, well, there is a rate of change of the flux, so I will have an induced EMF in the circuit, there should be a current. No. Using just an equation without really thinking about what is truly going on about the mechanism, yeah, you can get the it is possible to arrive to the wrong conclusion. There is no induced EMF. Using the two possible fundamental physical mechanisms will help you arrive at the correct conclusion. Using an equation without thinking about the mechanism may get you in the wrong conclusion, as it does in this case.